one important variable which may affect the performance of continuous sterilizers is the nature of the fluid flow in the system, as it has to go through the section for the holding period at sterilization temperature. Now ideally, all fluid which is entering the equipment at a particular instant should spend the same time in the sterilizer and exit the system at the same time, which would be the case of plug flow. No mixing should occur in the tubes. Now if the fluid near to the entrance of the pipe mixes with the fluid ahead of it, so if there are back mixing happening, then there will always be a risk that the contaminants will be transferred to the outlet of the sterilizer. So the type of flow in the pipes is desired to be plug flow. So there is neither mixing nor variation in the fluid velocity. So we know that the plug flow is an ideal flow pattern. In reality, the fluid elements in pipe have a range of different velocities. Now flow tends to be faster through the center of the tube than near the walls. However, the plug flow is approached in pipes at turbulence. Now Reynolds numbers above 2 into 10 to the power of 4, operation at such high Reynolds number can minimize fluid mixing and the velocity variations. So deviation from the plug flow behavior is to be characterized by the degree of axial dispersion in the system. So if we have to characterize the non-ideal behavior of the fluid flow, we must be able to characterize the degree of axial dispersion in this system. That is the degree to which the mixing is occurring along the length or the axis of the pipe. Now this axial dispersion therefore becomes a critical factor affecting the design of the continuous sterilizer. Now in order to find the relative effect of axial dispersion in this process, called as Pecklet number, which talks about the relative importance of axial dispersion and bulk flow motion during the transfer of the material through the pipe. Now if you see here, the Pecklet number is given here as U times L divided by the dispersion coefficient. Now U stands for the average fluid velocity, L stands for the length of the pipe of the holding section, and the denominator here is your axial dispersion coefficient. Now for perfect plug flow, the dispersion is 0. So therefore the Pecklet number would be infinitely high. Now in practical situations, the Pecklet numbers are found to vary from within a big range from very small values, singular values like 3 to 600. The value of the dispersion coefficients for particular systems, it further depends on the Reynolds number and the pipe geometry. So here for example, you can see a plot has been given between the Pecklet number and the Reynolds number, where how the Pecklet number changes with the change in the fluid flow shown here with the Reynolds number. And for different geometries, like here it is given for straight pipes, pipes with bends, or artificially roughened pipes or curved pipes. Now there is another dimensionless number which we call as Dahm-Kehler number. Now this dimensionless number, you can see the expression, it is given as KdL by U. So L we know is the length of the holding pipe, U was the average linear liquid velocity, and Kd was the death rate constant. So if you see the plot given here, the thermal destruction of the contaminating organisms has been defined as a function of the Pecklet number and the Dahm-Kehler number. So with the change in Pecklet numbers, the thermal destruction as a ratio given here N2 by N1 in the holding section is being plotted against the Damm-Kehler number, where N2 is the number of cells leaving the holding pipe, holding section, and N1 is the number of viable cells entering the holding section of the sterilizer. So, this figure shows that at any given sterilization temperature, which would then define the Damm-Kehler number, the performance of the sterilizer declines significantly as the Peclet number decreases. You can see from here the ratio of N2 by N1, it is going up as the Peclet number decreases, and the Peclet number decreases means there is higher axial dispersion. At a given sterilizer temperature, sterilization temperature would define your Damm-Kehler number, as Kd would be a function of temperature given the length of the holding section and the linear liquid velocity. And this N2 by N1 will be lower, which means better sterilization, greater level of cell destruction with higher Peclet numbers, which means lesser axial dispersion. So, what is to be noted here is that heating and cooling in continuous sterilizers are so rapid that in design calculations they are considered instantaneous. So, while reducing nutrient deterioration, this feature of the process can cause problems if there are solids present in the medium. Now, during heating, the temperature at the core of the solid particles will remain lower than in the medium. So, because of the extremely short contact times in the continuous sterilizers compared with the batch systems, there is a greater risk that these particles, if present, will not be properly sterilized. So, it is important that the raw medium is clarified as much as possible from such particles before it enters the continuous sterilizer. So, now let us talk about how filter sterilization or where it is used. We have been talking about steam sterilization. So, media containing heat labile components such as enzymes or serum, they can be easily destroyed by heat and therefore must be sterilized by other means. So, typically membranes are used for filter sterilization of liquids. Sometimes they are made of cellulose esters or other polymers. They have pores between 0.2 to 0.45 microns in diameter depending on the use. The membranes themselves must be sterilized before use, and sometimes they are one-time use membranes. As medium is passed through the filter, the bacteria and the other particles with dimensions greater than the pore size will be screened out and will get collected on the surface of the membrane. Now, smaller the pore sizes used in liquid filtration would mean that the membranes can readily be blocked unless the medium is pre-filtered to remove any large particles. So, to achieve high flow rates, large surface areas will be required. So, liquid filtration is generally not as effective and reliable as heat sterilization, because viruses or mycoplasmas, they are able to pass through the membrane filters. So, care must also be taken to prevent any formations of holes or tears in the membrane due to high pressure. Usually filter sterilized medium is incubated for a period of time before using it in order to test its sterility levels. So, after talking about the filtration of liquid medium or sterile liquid using steam sparging, even the air is being sparged in the fermenter. Now, this air which is being continuously sparged inside the fermenter also must be made sterile to avoid any contaminations during fermentation process. So, the number of microbial cells generally present in the air are of the order of 10 to the power of 3 to 10 to the power of 4 per meter cube. Filtration is the most common method for sterilizing air in large scale bioprocesses. Heat sterilization of gases is economically impractical. So, for sterilizing air, generally depth filters are used, which consist of compacted beds or pads of fibrous material such as glass wool, which have been used widely in the fermentation industry. Now, the distances between the fibers in depth filters, they are typically in the range of 2 to 10 microns and about 10 times greater than the dimensions of the bacteria or the spores which are required to be removed. So, it is very interesting to note that this kind of a setup is used to get rid of much smaller size bacteria present in the air. So, airborne particles, they penetrate the bed to various depth before their passage through the filter is arrested. The depth of the filter medium required to produce air of sufficient quality would depend on the operating flow rate and the incoming level of the contaminants. So, cells, they get collected in depth filters by a combination of processes including impaction, interception, electrostatic effects for particles which are smaller than 1 micron. So, cells get collected in these depth filters by a combination of processes including impaction, interception and electrostatic effects, and for particles which are smaller than 1 microns, diffusion through the fibers. The depth filters, they do not perform well if there are large fluctuations in the flow rate or if the air is humid or wet. The liquid condensing in the filter will increase the pressure drop, causing channeling of the gas flow and provides a path for the organisms to escape or grow in the bed. So, you can see the pictures of the depth filters shown here, and that is the magnification of the depth filter where you can see the pores and the fibers here, and see it's such a complex network of fibers through which the air passes through for filtration. So, here in the schematic, the 3 processes are shown here: interception, diffusion, the impaction. You can also make note that the size of the particles is different for different process by which they are getting removed or getting held in the filter. So, increasingly depth filters are being replaced for industrial applications by membrane cartridge filters. These filters, they are steam sterilizable polymeric membranes which act as surface filters, trapping the contaminants as on a sieve. So, membrane filter cartridges, they typically contain a pleated configuration as shown in the picture here, which will allow a high filtration area to be packed into a small cartridge volume, and hydrophobic filters will minimize problems with the filter getting wet. Small and uniformly sized pores, which is nearly 0.45 microns or less in diameter, are present on these membrane filter cartridges. Pre-filters can be built in these cartridges or upstream, which can reduce the fouling of the membrane by removing the large particles, like for example air or water droplets or foam in the incoming gas. Filters, they are used to sterilize also the effluent gases leaving the fermenters. Apart from the sterile air which is being sparged in, there is a continuous outlet of air from the headspace to release pressure. So, that effluent gas is also sterilized, passes through these filters before it moves out of the fermenter. The objective is to prevent release into the atmosphere of any microorganisms which gets entrained in the aerosols through the headspace of the reactor. The concentration of cells in the fermenter of gas is several times greater than in the air which is coming inside. So, containment becomes particularly important when organisms used in fermentation are potentially harmful to the human personnels which are working or the environment. Companies operating fermentations with pathogenic or recombinant strains, they are required by the regulatory authorities to prevent the escape of these cells. So, if we need to characterize the efficiency of the air filtration process, we must first see how the three processes impact the removal of the organisms. So, inertial impaction, this is the particles in the inlet airstream of the filter can get impacted due to mass being sufficient, due to sufficient particles in inlet airstream of the filter. If they have enough mass, then they will have sufficient momentum to break away from the diverging streamlines across the fiber, and they will continue in the same direction to directly collide with the fiber and get trapped. So, if you see the schematic here, you can see the impaction process shown here. If it has enough mass, due to the momentum it gains, it can continue to move in the same direction, deviating from the streamlines, and can get stuck in the fiber. Now, Stokes number is generally used to classify the potential whether the particle will be collected by inertial impaction or not. Now, this would be dependent on the flow velocity and the particle diameter. So, the collection efficiency by the inertial impaction mechanism is given as a function of the Stokes number and Reynolds number. Efficiency would increase with the increasing particle diameter and the airflow velocity. So, impaction efficiency, if it is defined as EI, it is a function of Stokes number and it increases as the Stokes number increases. So, here for Reynolds number equal to 10, an empirical relationship for the inertial impaction efficiency is given here in terms of Stokes number, and for other than 10, the efficiency of impaction is being defined by the second empirical equation. Similarly, if the particle is getting trapped by the interception process, what does that mean? It means that the particles having big size but less mass, they will follow the streamline of air as they diverge around the fiber collector. However, they can get trapped if they are close enough to contact with the fiber. So, if you see the schematic, here it is shown for interception. The particle is large in size, but the mass is not heavy. So, it is being carried by the streamline of air, and because of its size, it may interact with the fiber and get stuck. So, the efficiency of interception would depend on the ratio of the particle diameter to the collector diameter, the fiber diameter. So, interception parameter has been defined here as the ratio of the diameter of the particle to the diameter of the collector, and in turn it can be a function of the Reynolds number and the interception parameter. So, this is one empirical relationship shown how to define the efficiency due to interception. Efficiency means the collection efficiency. So, one can make out the collection efficiency would increase with the increase in the particle size. Now, if the particle size is very small, then smaller than 1 micron in diameter, they will exhibit Brownian movement, which will be sufficiently intense to produce diffusion. Now, if a streamline containing these particles, they are sufficiently close to the collector, the particle might hit and then get trapped. So, the collection efficiency by diffusion will increase with decrease in particle size or the air velocity, the bulk flow. So, here the efficiency due to diffusion has been found to be function of the Peclet number and the interception parameter. So, here the Peclet number in turn is made a function of the Reynolds number and the Schmidt's number. The diffusivity due to Brownian movement is your dBr for submicron size particles. So, you may call it as convective diffusivity. So, the efficiency due to diffusion is a function of the Peclet number here, has been defined as an empirical relationship being a function of Peclet number and the Boltzmann constant. The Peclet number in turn being a function of Reynolds number and Schmidt's number. The Schmidt's number is being defined by the convective diffusivity due to Brownian movement, which would depend on the diameter of the particle, and the Boltzmann constant, where K in the diffusivity function is the Boltzmann constant, Cf is the correction factor, in turn being given by this function shown here. Now, if we need to calculate the overall efficiency of impaction or interception or by diffusion, the efficiency for collection of the particle by the filter can be obtained if we know the individual efficiencies of impaction, interception and diffusion. So, the probability of successfully collecting the particle by one or more of the mechanisms, then we first calculate the probability of particles not getting collected by one but getting collected by any other mechanisms. So, 1 minus eta IMP would be the probability of not getting collected by impaction. 1 minus eta INT would be the probability of not getting collected by interception. Similarly, 1 minus eta DIF would be the probability of not getting collected by diffusion process. And the overall probability of not getting collected by any of these processes will be multiplication of all these probabilities. And if we reduce this by 1, then it will be the probability of being able to collect by one or more of these mechanisms. So, your overall collection efficiency, here it is being given by an empirical correlationship defined by the Schmidt's number and the Reynolds number and the interception parameter. So, with the increase in the superficial air velocity, the efficiency due to impaction and efficiency due to interception would increase, whereas the efficiency due to diffusion might decrease.